right, so let's take a look here. What we want to do is use local linear approximation. So basically, we want to use L of x, okay, for the given function f of x being equal to the cubed root of x at a given value where x is equal to 8. And what we want to do is use it to approximate the cube root of 8.1. Okay, so if I ask you, what's the cube root of 8? 2. What's the cube root of 8.1? It's probably a little more than 2. Agree? Okay, but if I wanted you to give me a more comprehensive approximation, meaning I want a little bit more than the explanation of a little more than 2, that's what we want. We want a decimal value. Okay, so this is what we want to do first. We want to use this right here. Our function, which, can you picture the graph? What does the cube root of x look like? It does have a vertical tangent line at 0. But what does a graph look like? A stretched out S, right? That goes through the order. Yes, absolutely. And if I asked you to find the cube root of 8, you could totally do it, right? And what we want to do is find an equation of a line that is tangent to the curve at 8 and use that formula to approximate the cube root of 8.1. So, in order to find an equation of a line that is tangent to this curve at x equals 8, what do I need? A point and a slope. So let's find the point. We want to evaluate f of 8. What's f of 8? It is 2. Right? Okay, so we have the point 8, 2. Okay, now we need a slope. How do we find the slope? We need to take the derivative. So we have f of x is equal to x to the 1/3 power. We're going to take the derivative. F prime of x is equal to what? 1/3. Okay, so I'm going to rewrite this as 1 over 3x to the 2/3 power. This is my derivative. Let me give you guys a little bit of advice. Some of you are having issues writing or rewriting a rational exponent in terms of a radical. Don't bother. Just leave it as a rational exponent. Some of you don't remember or forget or kind of go crazy when you're taking a quiz and you put the root and the power in the wrong places, or the root looks like a coefficient. Just leave it as a rational exponent. It's totally fine. This is acceptable. Okay, so if this is the derivative, what am I using this for? To find the slope. And I want to find the slope where? At 8. So that means I need to evaluate, let's go up here, f prime of 8. So I've got 1 over 3 times 8 to the 2/3 power. What does 8 to the 2/3 mean? Not what is the value, but what does it mean? Okay, what is the cube root of 8? Cube root of 8 is 2. 2 squared is, times 3 is 12. Yes, from the problem. So what is 1/12? What is that? It's my slope. Do I have everything I need to write the equation of the line that's tangent to the curve? Okay, so we've got y minus 2 is equal to 1/12 times x minus 8. Equation of the line tangent to the curve at 8. True? Okay, now, remember, we want to make this look fancy. It needs to say L of x. So what is the first thing I need to do? I need to add 2 to both sides, and then can I replace this y with L of x? That's how we make it fancy. It's the linear approximation, because this would say y is equal to, I want this to say L of x is equal to 1/12 times x minus 8 plus 2. This is our linear approximation formula, L of x. And what we're going to do with this is use this linear equation to approximate the cube root of 8.1. So we're going to evaluate L of 8.1. So we have 1/12 times 8.1 minus 8 plus 2. So this is 1/12 times 0.1 plus 2. Okay, in this case, it would be challenging to do with without a calculator, right? So we're going to use a calculator, and I'm going to calculate this value. So it's Okay, this is what I got. So this is the approximate value of the cube root of 8.1. Now, typically in this class, you guys take the decimal out to 4, but in order for us to identify if this value is an over or under approximation, we need to go out a little bit further, and I'll show you why in just a minute. So we're going to say that L of 8.1 is equal to 2.0083, and we know that's repeating. I mean, you can write as many 3's as you want, but it's going to keep going. Okay, everybody good with the calculation first? Yep.
Why'd you do L of 8.1 instead of 8.1 with the cube root of 8.1?
Because we're using linear approximation to get the cube root of 8.1, and I'm going to show you how that works. So what we're trying to do is use a linear equation to approximate the value of a decimal at some given function. So now what I'm going to show you is how crazy this is. This is why I'm saying this totally blows my mind, that I can use a line to approximate the value of the cubed root of cubed root of 8.1. Because watch what happens. If I take 8.1 to the 1/3 power, which is the cube root, how crazy is that? To me, that's totally crazy that I can take the cube root or any function evaluated at any value, and if I zoom in close enough to that point or the nearest whole number to that point, I can use a linear equation to get that. To me, that's crazy that it actually works. Because, I mean, look at how the discrepancy is so small, it's negligible. Agree? Okay, I don't know. Am I the only one that thinks that's crazy? I mean, I just, thanks, man. I appreciate it. Okay, so here we know that f of 8.1, I need all the support I can get, so I appreciate it, 2.00829885. And I wrote all that out because what I'm asking you is L of 8.1 an over or under approximation? Okay, this is an over. I'm just giving an arrow because I ran out of room. This is an over estimation or approximation depending on the word. Okay? Now, tell me why you think that is based on what I told you on the previous page. What can you speculate? Yes?
Concave down.
Exactly. F of x is going to be concave down at 8.1. So F of x is concave down. I'm going to show you something. I sketched this out just so you could see. This is my graph. At 8.1, the graph is concave down. There is my linear approximation formula. So any value that I use that line to approximate here in this vicinity, in this domain, from 0 to whatever those values are, it's concave down, right? F of x is concave down. Is that going to change if it's here? This is concave up, right? So then the line is probably going to be below based on our pattern. Does everyone understand what I'm saying? Okay, does anyone have any questions about the process? There's almost nothing that is different. It is pretty much the same as what we learned in Unit 1. Okay, so here's the process. Here we go. Find the local linear approximation L of x. As soon as you see local linear approximation, you know you need to find an equation of a line that's tangent to the curve. That is your cue. That's the clue as to what you need to do. You're given the function and you're given an initial value of x at 1. Okay, I'm going to stop there because if I need a line to approximate a value, what do I need to do? What is the process? Find the point, find the slope, put all the pieces together, right? Write the equation of the line. All right, so I need to evaluate f of 1. What is f of 1? It's negative 1. 2 times 1 cubed, which is 2, minus 3 times 1, which is negative 3, so this is negative 1. So here's my point, 1, negative 1. Everybody okay? Okay, to find the slope, what do I have to do first? Take the derivative. F prime of x is equal to 6x squared minus 3. Everybody good? Now what? Plug in 1 to find the slope. So evaluate f prime of 1, which is 3. Does everyone agree to that? So this is equal to m. All right. Do I have everything I need to write the equation of the line? Yes. So it's y plus 1 is equal to 3 times x minus 1. Okay, what am I going to do with that? Subtract 1 and, yep, replace the y with the L of x. So we're going to make it look a little different. So we have L of x is equal to 3 times x minus 1 minus 1. This is my local linear approximation formula. Okay, so now what they said is use it, meaning L of x, to approximate L of 0.99. Okay, so L of 0.99 is equal to 3 times 0.99 minus 1 and then minus 1. What is 0.99 minus 1? Okay, so we have 3 times negative 0.01 minus 1. Isn't that negative 0.03? Minus 1, so this is negative 1.03. Is that right? That is my linear approximation. What that means is, instead of taking 0.99, cubing it, multiplying by 2, and then subtracting 3 times 0.99, all without a calculator, have fun, I got the value. But do you see what I'm saying? Like, we could do this without a calculator. It was very easy, right? Because they were common things that we should know how to do. This, if I plug in 0.99, it would be more challenging. It's going to take up a lot of paper because I'm not allowed to use a calculator. But now I'm letting you use a calculator because what do I want to see? Yes, if this value is an over or underestimation. Now, we're dealing with negative numbers. We need to be very careful how we make this statement. So, my suggestion to you is, for those of us that have forgotten, if you go into y equals and you put the function in that you're given, 2x cubed minus 3x, and I go into second window, this is where I can change the calculator from auto to ask. Because then I can go into the table and just plug in 0.99. If I just go into the table, it's going to go 1, 2, 3, 4, 5, 6, 7, and that doesn't help me. Okay, so you need to remember how to use a calculator. So you go into second graph. I already plugged it in. Now, if I look here, I don't have very many decimal places. However, if I move this cursor over and I highlight this, it takes it out further so I can compare. Does everyone see what I just did? Okay, so now, when I evaluate f of 0.99, I get negative 1.029402. That's out far enough where I can compare. So if you need to make a note here, we found this in the calculator. This one right here. So you need to tell me, is L of 0.99 an over or underestimation? Be very careful how you answer this question, George.
It's an underestimation because it's a negative number. So
yeah.
A larger negative number, I don't know if that makes sense.
The closer to 0 you are, the bigger the number in terms of negatives.
Yeah.
This is smaller than this. How's that?
That works.
Yeah. So this, meaning L of 0.99, is an underestimation. And graphically, what can you say about f of x? Is concave up. That is true. Okay, so I'm going to show you the graph. Now, this is what the graph of the entire function looks like, approximately. This is just a sketch. So there are multiple areas where the concavity changes, right? But because we are talking about 0.99, which is in this region somewhere, my linear approximation falls here, so the graph is concave up. Therefore, my linear approximation is below, meaning an underestimation. Does this make sense? Questions? So there are two small things that are different about finding the equation in order to find your answer and over or underestimate. But other than that, it's writing an equation of a line that's tangent to a curve. Does anyone have any questions that they want to ask about that before we move on to differentials? Okay. Up to this point, when we were taking the derivative, some of us were using f prime of x, y prime. we started to move into dy dx. And we talked about the meaning of dy dx with respect to the slope, the change in y over the change in x. But other than that, we really just used dy dx as a notation. Each one of these separately or independently, if you separate dy dx, dy and dx are known as what's called differentials. And really what they are approximations in the changes in x and the changes in y. That's why dy dx, if you use it as a slope, it's delta y over delta x, right? All of this is interchangeable. But what we're saying is there is a change that we are approximating, is an approximate change indicated by that notation. Okay, so that is what we're using differentials for, to indicate a possible change in area or change in circumference. So dA, we're stating, could be potentially a change in our area. DC could be a possible change in our circumference of whatever circle we're talking about. So now what we're doing is we're attaching meaning to that differential so that we can use it for something. Everybody good? That's really all this is saying. And we implied it when we were talking about the slope.